On July 27, 1918, a powerful explosion occurred at a testing ground on the Quiberon Peninsula in France, the sound of which was heard from a distance of several miles. A pillar of flame was observed, and the shock wave extended over a radius of several hundred yards. After the smoke cleared, it was determined that the 20.47-inch howitzer, weighing 290 short tons, and being one of the largest artillery systems, was completely destroyed. The gun failed during test firing. A shell weighing 3,020 pounds burst inside the bore. This incident was the first in the history of the operation of this type of weaponry. The history of the development of this system began earlier, in the context of strategic planning by the French military command. By the beginning of the First World War, French military doctrine was based on the concept of an active offensive and a rapid conclusion to the conflict. Plans envisaged the use of infantry and maneuverable units to break through enemy defenses and advance deep into their territory. Heavy artillery was viewed as a low-mobility type of weaponry, capable of slowing down the pace of an offensive. Priority was given to light, rapid-fire guns, particularly the 2.95-inch field gun. However, during combat operations towards the end of 1914, the situation changed. The front stabilized, and a continuous line of fortifications formed from the North Sea to the border with Switzerland. The sides shifted to positional warfare with the construction of fortifications made of concrete and steel. Light artillery proved insufficiently effective against the fortifications of the German army. The opposing side, using heavy artillery, inflicted significant damage on French positions. Under conditions of significant destruction of defensive lines and loss of personnel, the French command revised its approach to artillery armament. The development of high-power systems began. A decision was made to develop railway artillery mounts. This step offered logistical advantages over towed guns. Rail transport ensured the delivery of heavy howitzers to positions regardless of weather conditions and the state of dirt roads. When necessary, new tracks were laid, which was possible under the conditions of the positional nature of the war. Manufacturers, including Schneider, began producing a line of railway mounts with calibers ranging from 6.46 to 14.57 inches. In many cases, adapted naval guns were used. The Saint-Chamond Company developed a 15 3/4-inch mount, which demonstrated high effectiveness in application. At the end of October 1916, the use of this gun led to significant results. German troops had occupied Fort Douaumont, reinforcing its defenses. Assaults undertaken by the French command using infantry regiments did not bring success. Subsequently, a 15 3/4-inch howitzer was delivered to the fort. After 2 shots with 1,433-pound shells, part of the fortifications was destroyed. German units abandoned the positions in the adjacent sector of the front. The effectiveness of heavy artillery actions prompted the French military command to consider the possibility of creating guns of a larger caliber. On January 24, 1916, the Schneider Company received an order for the development of new artillery systems. The technical specifications provided for the creation of 2 railway howitzers with a caliber of 20.47 inches. It was assumed that this weapon would be capable of destroying enemy fortifications with single shots. Schneider engineers faced a complex technical task, as they had to create a system that had no direct analogs. The adaptation of ready-made naval guns used in previous projects was impossible in this case. The French Navy and Army lacked guns of such a caliber. The development process, from the barrel to the loading system, was conducted from scratch. All design elements required calculations and engineering solutions that had not been applied previously. The design took more than a year. Special attention was paid to details and calculation accuracy to prevent accidents. The barrel, 39 feet long, 15 calibers, weighed 48.5 short tons and was a solid cast steel structure designed for high powder gas pressure. The total length of the railway platform with the gun exceeded 98.4 feet. The system was based on two paired four-axle bogies that distributed the weight across the railway track. The total mass of the unit was 290 short tons, making the howitzer one of the heaviest artillery pieces. One of the main technical difficulties was the aiming system. The angle of elevation varied in the range from 20 to 60 degrees, which allowed for high-angle fire. Horizontal aiming was complicated by the impossibility of creating a turntable for a mass of this magnitude. As a result, a technical solution was adopted. For horizontal aiming, the entire 290 short-ton unit was moved along specially laid curved railway tracks. This required significant preparatory work at every firing position. The loading process was a complex technical operation. To perform loading, the barrel was moved to a strictly horizontal position. The projectile was fed to the breech by a special electric-driven mechanism. Due to the mass of the ammunition, ranging from 3,020 to 3,646 pounds, manual labor was excluded, so a system of electrical mechanisms was developed to service the howitzer. The system's power supply was provided by a separate railway car with an electric generator with a capacity of 103 kilowatts. Without external power, the operation of the gun was impossible. Separate loading was used. First, the projectile was fed into the barrel, then the propellant charge. Two types of high explosive ammunition were used. Projectiles weighing 3,020 pounds had a muzzle velocity of 1,640 feet per second and a firing range of up to 10.6 miles. Concrete piercing ammunition weighing 3,646 pounds was intended to destroy fortified objects. Their muzzle velocity was 1,411 feet per second, and the firing range was limited to 9 miles. The reloading cycle took at least 5 minutes, which resulted in the howitzer's low rate of fire. Preparing the firing position was an engineering operation that took several days. Standard railway tracks were not designed for such loads. Laying additional sleepers was required to reinforce the foundation. Steel beams were placed on the rails to distribute the weight of the gun. 7 supports of the railway unit were lowered onto these beams using screw jacks. 5 supports were located under the middle part of the platform, directly under the gun, taking the main load. 2 additional supports were located under the balance beams of the undercarriage. This system was intended to ensure stability during firing and compensate for recoil when using heavy shells. The first howitzer was manufactured by November 11, 1917. Assembly took about 2 years. The second unit was completed by March 7, 1918. The French command organized large-scale tests involving the press for propaganda purposes. The goal of the event was to boost the morale of their own troops and demoralize the enemy by demonstrating the presence of weaponry with high destructive power. Tests began in February 1918 and continued into March. Reports on the firing were published in the press with calculations of the potential damage the gun could inflict on enemy fortifications. Photographs of the gun were published in major French print publications. It was expected that the use of this artillery system would influence the course of hostilities. On July 27, 1918, a group of military observers and press representatives was present at the testing grounds on the Quiberon Peninsula. Weather conditions were favorable for firing. The first howitzer, which had previously undergone a series of tests, was being readied for a shot. The crew completed preparatory operations, and the shell and powder charge were placed in the barrel. Soon after this, an incident occurred that led to the destruction of the gun and became one of the major catastrophes in the history of artillery operation. After the crew commander's command to fire, a shell weighing 3,020 pounds exploded inside the barrel bore. The blast wave destroyed the 48.5-ton barrel. Metal fragments flew in all directions. A fire broke out over the testing grounds, followed by secondary detonations of ammunition and fuel. The railway platform was deformed, and the loading mechanisms were destroyed. The artillery mount was completely destroyed, and its debris scattered across the grounds. The investigative commission could not establish the exact cause of the incident. Versions considered included a manufacturing defect in the ammunition, structural flaws in the barrel, or a combination of factors. As a result, France lost half the arsenal of these howitzers before their combat use. The results of 2 years of engineering work and financial costs were lost. The second howitzer had completed tests by this time and was in the arsenal. After the incident at Quiberon, the command considered options for further action. The gun demonstrated high power during test, however. The accident pointed to possible design flaws. Meetings were held regarding the advisability of operating the remaining unit. During the discussions, the war came to an end. On November 11, 1918, an armistice was signed between Germany and the Entente countries. The First World War ended, and the gun was not used in combat operations. The howitzer was sent for storage in Le Creusot and then to the heavy railway artillery arsenal in Neuvy-Payloup. Spare barrels, ammunition, and substations for powering electrical systems were also placed there. In the 1920s, the weapon featured in French military propaganda. Photographs of the howitzer were published in the press. Military observers described the gun's power and its capabilities for destroying fortifications and urban structures. The howitzer was demonstrated as a symbol of military might, and foreign delegations visited the arsenal. At the same time, the gun remained in storage and was not used in real conditions. The situation changed in the spring of 1940 with the start of the German troop offensive against France. The advance of troops proceeded at a rapid pace. German tank formations broke through the defense and advanced deep into the country. The French army, oriented toward positional warfare, faced the tactics of maneuver warfare. The Maginot Line was bypassed by German troops through the territory of Belgium. The French command attempted to organize resistance. However, the pace of the German offensive prevented the creation of a stable defensive line. In the conditions of retreat, the particularly large caliber howitzer, located in the arsenal at Neuvy-Payloup, remained at the storage site. Preparing this gun for combat use required several weeks. It was necessary to lay railway tracks to the firing position, reinforce the roadbed, install supports, connect a wagon with a generator, and deliver ammunition. The speed of the front line's advance made these preparations impractical, as by the time of readiness, the gun would have ended up in the rear of the advancing troops. On June 22, 1940, France capitulated. German troops occupied the arsenal, getting at their disposal a 20.5-inch howitzer in combat-ready condition, which the French side did not manage to employ. The German command assigned the captured gun the designation 20.47 inches Haubitz E871F. German engineers studied the design and checked the condition of the mechanisms. Despite long storage, the technical condition of the howitzer was assessed as serviceable. The gun had undergone regular maintenance. Along with the artillery mount, spare barrels, ammunition, and deployment equipment were captured. The gun was regarded as a significant reinforcement of the artillery park. In the summer and autumn of 1940, preparations began for its transport to the Eastern Front, where the use of the howitzer was envisaged during the siege of cities and fortified areas. Transporting the 290 short-ton object across European territory required planning. including checking the load-carrying capacity of bridges and railway tracks, as well as organizing route security. By the summer of 1941, by the beginning of hostilities against the Soviet Union, the gun was en route. The Wehrmacht offensive developed rapidly. Panzer groups occupied territories and surrounded enemy formations. By September, units of Army Group North reached Leningrad and began preparations for blockading the city. The German leadership decided to abandon the storming of Leningrad in favor of a blockade and artillery bombardments. It was decided to use the captured French howitzer for these purposes. At the end of October 1941, the gun arrived in the Leningrad area. A position allowing fire on city targets was chosen. Engineering works began to prepare the firing point. Sappers laid access tracks, reinforced the roadbed, and installed supports for the platform. Parallel preparations were made for ammunition and connecting auxiliary equipment, including a generator for the loading mechanisms. Work was conducted under conditions of potential opposition from Soviet aviation and artillery. German artillery crews underwent special training to operate the captured gun. The process included studying French technical documentation, mastering control mechanisms, as well as practicing procedures for loading and aiming. The system's design differed from the armament patterns familiar to the personnel. Operations required adherence to instructions and coordination of the crew's actions, since errors carried risks for personnel and could lead to damage to the materiel. By the beginning of November, training was completed. The howitzer was deployed at the firing position in readiness to fire on Leningrad. The German command planned to use the gun to destroy city targets. Shells weighing 3,307 pounds were intended for the destruction of industrial infrastructure, communication nodes, as well as for impacting the morale of the garrison and population. Concrete piercing ammunition weighing 3,646 pounds, calculated to destroy fortified structures, was also employed. Sequential destruction of targets and inflicting significant damage on the urban buildup was planned. Firing began in November. The shells covered a distance of several miles and fell within the city limits. Exploding munitions formed large craters and caused destruction within a radius of dozens of yards. The shock wave affected the glazing of buildings at a significant distance from the epicenter, and fragmentation spread was also recorded. Hits inflicted substantial damage on the shelled areas, however. Effectiveness was limited by the system's low rate of fire. The technical capability was 1 shot every 5 minutes, up to 12 shots per hour, but the actual rate of fire was lower. Intervals between shots were required for inspecting the bore, checking mechanisms, and preparing ammunition. The loading process was a multi-stage operation. The barrel was moved to a horizontal position. The shell and charge were fed to the breech by electric mechanisms, after which the necessary elevation angle was set. The position of the high-power artillery system was discovered by Soviet troops. Counter-battery units returned fire to destroy or damage enemy artillery. The German side built protective structures around the howitzer, camouflaged the position, and maintained a state of readiness. Soviet aviation also attempted to bomb the gun, but anti-aircraft fire and Luftwaffe fighters reduced the effectiveness of the raids and increased the risks for the attackers. In December 1941, the weather conditions were characterized by low temperatures. Frosts reached -22 degrees Fahrenheit, which created technical difficulties for the howitzer crew. Freezing mechanisms and thickening lubricant increased the time and effort required to perform operations. Nevertheless, the shelling continued. Fire was conducted methodically on designated targets to inflict damage on the city's defenses. On January 3, 1942, in clear weather and low temperatures, the gun crew prepared to shell positions near Leningrad again. Operations were carried out according to the procedure established over the previous weeks. A shell weighing 3,020 pounds was lifted by an electric mechanism and placed into the bore. Then the powder charge was loaded. The barrel was raised to the specified elevation angle. The crew commander gave the order to fire. At that moment, a malfunction occurred. The shell detonated inside the barrel. A similar incident had occurred 24 years earlier at the French Quiberon proving ground. The explosion destroyed the 48.5 short-ton barrel. As a result of the blast wave, the railway platform was deformed and the loading mechanisms were destroyed. The second 20.5-inch howitzer was put out of action due to the detonation of its own ammunition, just like the previous unit. The incident resulted in the total loss of the gun's combat capability. The artillery system, intended for use in the siege of Leningrad, could not be repaired due to critical damage. The wreckage of the unit remained at the position until it was discovered by Soviet troops in 1944 during the occupation of the area. This marked the end of the operation of the largest caliber gun of the First World War period. Both specimens were lost as a result of internal explosions without realizing their design potential. This case illustrates the risks of engineering projects where the pursuit of maximum power can lead to technical failures and make safe operation impossible. You can suggest examples of military equipment for review in future episodes in the comments. Audience engagement is taken into account when preparing new material.